Welcome. This is Wednesday, June 8th, our class session, and Math 264 at Delta College. We get to bring several things together today, so it should be a fun day. And these are the highlights of today, and we'll visit our website, and we visit our whiteboard for a little while this morning too. So the linear systems we're doing are really, really important. I'm not entirely ready to tell you why they're so important. At first, they just seem like a curious, fun thing to do because there's a nice mechanical way to write down solutions. But why is that so important? You know, there's a mechanical way to mow your lawn too, but nobody thinks that mowing their lawn is a very fun thing. Or, apart from, making your lawn look nice, what's the value of it? Today, we're going to look at what happens if we have complex eigenvalues. And so that involves some intense arithmetic, but not as bad as you might consider it to be. So I don't know how you've worked with complex numbers in the past, but yep, they're numbers. You can add, subtract, multiply, and divide them. And what we're going to get into is classification of linear systems. And that's the beginning of telling you why linear systems are important. And so that's on the whiteboard. I think we'll travel to the whiteboard in a second, just to make sure that you're starting to see the big picture. Okay, questions that I generally have received over the last several hours. You've been reading your tests, so thank you, good work on that. Remember, you have your grade report, so you can always calculate your current grade and what you could do with your current grade. And I'm not trying to be discouraging at all. So, if we front loaded this course, the extra homework problems and things like that, we've front loaded this course so you can clean up and get faster and better as you go along. So let's focus, do your focus on the homework problems, on knocking out a lot of fives. Focus on practicing and looking and reading the recommended problems. So you can still do whatever you need to do in this class. Anytime you're doing anything, you always want to do it better. And you're usually never personally satisfied, or I guess sometimes we should be personally satisfied. But you have plenty of time to work in this class, point-wise. Of course, on the calendar, we only have 3 weeks after tomorrow. So it's what I'm going to say, finish strong in the class. I also want to say, when you're sending me questions, and you are not the only one who ever asked that question, no matter what it is, you are not the only one who ever asked, what can I improve this grade? Can I do this problem? People all ask the same questions. So I want to make sure when I respond to you in the email, as I respond to you, many of you, with this same phrase, check the website, do the recommended problem, check this handout. I am not criticizing you for not reading the handout. I am not picking on you for not seeing that recommended problem. I'm just directing you to them, right? So face-to-face communication is much easier. It can be much more pleasantries, smiles, fun, all kinds of things like that. But in this space, I got to just be very direct and very quick. I try to be as direct as possible. And that is, make sure when you're trying to do a problem, when you're trying to research a problem, even on the exam, first thing you should think about is, what is this problem like? Has he done any other problems like this or close to this? Because they're not going to be exact copies, but focus on, and you guys are doing a good job of that. Focus on identifying the type of problem and how to execute that type of problem. So remember your resources. resources page, and resources among the recommended problems. So never, ever, when you ask a question, take it as a criticism if I say, check out this problem, or did you see this problem? I'm not criticizing you at all. Or if I write on your paper, consider doing it this way. I'm just trying to make sure that you haven't missed something, because if we were together, I would be handing out lots of pieces of paper, making eye contact, stuff like that. Okay, so always practice things on the website, videos and handouts. To that end, I'm going to start on handout, or I'm going to start on the website right now, just to show you what I mean. So I'm going to share screen. I'm going to come over here to website. Where am I? Good, got it. And I need to make sure. Okay, no, that's good. We're looking at the linear systems website. If you were here before I hit the recording button, I showed a brief mention of my studio, or what you might call my studio. And I have the iPad kind of telling me what you see. So we're looking at our webpage. So these linear system handouts are golden, golden. And the videos, linear systems basics, linear systems real and non-zero eigenvalues, linear systems complex eigenvalues, bifurcation, those are very, very valuable. So I am going to just scan these linear system handouts with you right now. I'm not going to click and yank them from the Google Drive, because I always have that issue of lag because of how I'm using the network right now. But I have put them on my desktop, all 13 of those handouts, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes. And I'm going to share them with you right now. So I am sharing them with you, and I'm not sharing them with you to read them or to make you read them. I just want to run through these to make sure you know that they're here. It's critical. So among all those linear system handouts, first I give you an introduction, which tells you how to translate to matrix, tells you trace, determinant, characteristic equation, and eigenvalues, the most important things about a square matrix. Trace, determinant, characteristic polynomial, characteristic equation, and the eigenvalues. So the 4 things that would be printed on the driver's license of this matrix. Then page 2, handout 2, single page handout, talking to you about what an eigenvector is philosophically and practically. So here we show you what an eigenvector is, that unique vector associated with that unique value of the matrix. So when does matrix multiplication end up the same as scalar multiplication? It's kind of an unexpected thing. Handout 3, how do you physically construct eigenvectors? And here's where I use that idea of subtracting lambda on the main diagonal and switch and change sign. That is a very simple and quick way to construct an eigenvector in 2-dimensional space. Now, if you take a future class, linear algebra class, 3, 4, 5 dimensions, this switch and change sign works in the 2-dimensional case. So we're talking about a special case, but it's an easy way to construct eigenvectors in this case. I do not have many concerns about our book. This is one of the most excellent books ever written in this subject. But sometimes when he talks about constructing eigenvectors, he refers back to linear systems calculation. It's not a problem, but I think he says sometimes too much. They, the 3 authors. An eigenvector in the 2 by 2 case is simply creating a perpendicular vector to the rows, the multiple rows of the adjusted matrix. And then the 3 tips, which I highlighted in a previous day. Select the coordinates with no common factors. In other words, reduce your factors. Don't select fractions unless you have to. There will be a time where you have to. And tip number 3 for constructing eigenvectors. 0 and 1 are your friends. Use them whenever you can. Why do I say 0 and 1 are your friends? Because when I'm working through calculations and I want to do them in a fast and efficient way, it's always easy to multiply by 1 and to add 0. So why not pick 1, 1 instead of 7, 7 for an eigenvalue, right? Okay, next step. We can compare the work we did solving second order linear equation with first order linear system and see that this guess and test method, the e to the st method, is really the same as the eigenvalue eigenvector method. So here I just executed a problem side by side so you could get a feeling for solving the first order linear system is the same as solving second order linear equation. But this will be more important to us as we go along. Then we'll do a detailed graphical presentation of the cases. First cases that we've knocked out in section 3, sink saddle source. And I didn't draw both sides of the straight line solution, but I did try to show you a generic slope field, streamlines, and half of the straight line solutions, or you call them straight line rays, or I could call them the straight ray solutions, but most people call them straight line solutions. So sink saddle source, identifying by different colors, and you can tell by looking at the way things flow when you have a saddle. Sometimes, unless you see the arrows, you can't tell whether you have a sink or a source. And then we're going to advance. So I got this a little bit out of order today. Today we're going to go to complex eigenvalues. And complex eigenvalues mean that we're going to be growth or decay together at the same time with oscillation. And if you think about what that would mean in the plane, oscillation means you're revolving about the origin. Growth or decay means you're spiraling in or spiraling out. But there could be lots of oscillation and slow growth or decay, or there could be slow oscillation and lots of growth or decay. Or in this third picture down here, if you had to describe this, I think what you have is oscillation with neither growth nor decay. So think about these things physically as in pictures. And then further cases that we'll examine later today and tomorrow, possibly special cases. I'm not going to talk about these sheets yet, because we'll talk about them later. And then this concept of how could we classify linear systems. Anytime you can classify something, you've arrived at a great place. It's like you have command over that subject when you can classify something. And I'm going to give you multiple ways to classify the two-dimensional systems. So here's a little tree diagram, so you could follow this. But I think this is a little bit cumbersome. The most awesome way to classify something is visually or graphically. And so even though you don't know exactly what all these words and symbols mean yet, and we won't present this fully until Monday, here is the simplest way to classify two-dimensional systems. Think of them in the graphical representation. Finally, since you got to be totally awesome at doing all two-dimensional systems, what I did in this last handout in the series is just give you a pile of matrices and just, say, like they say in the military, drop and give me 20 push-ups. Anytime you look at a matrix, you should immediately write down its trace determinant if it's a square matrix. eigenvalues, eigenvectors, and then you can form, in the case of the first order linear system, the general solution, and you can classify it. So here are 12 separate examples of different things you can practice classifying. Trace and determinant have to be automatic with you, and then they automatically produce eigenvalues. Those things you should be able to fill in within seconds. The general solution requires the computation of eigenvalues or eigenvectors, or what we'll talk about later, almost eigenvectors. But classifying it can be done instantly from trace and determinant, as we will see. Since this is like a practice sheet, I then provide you with the answers right here, but I scrambled the order of the problems, like when you're doing a crossword puzzle in the newspaper, and or a cryptogram in the newspaper when they print the answers upside down. So even though you can look at them, you can't focus on them. It's distracting, so it discourages you from looking at the answers. So here are problems you should be able to snap out relatively quickly. General solution is the one that takes some kind of computation. And then here are the answers that you will check them against. Okay, that is that pile of handouts. That pile of handouts is very, very valuable. Scrolling through them doesn't give you any skill whatsoever. Even reading them doesn't give you any skill. It's doing them that's going to give you the skill. And my favorite silly illustration is I've read many novels, right? Don't ask me to write a novel. I'm not going to write any kind of clever, wonderful novel, right? Because I haven't practiced writing novels. I'm a big basketball fan, baseball fan. I was kind of the Magic Johnson era. Even go back to the Jerry West era, the Wilt Chamberlain era. Well, let's just talk about Magic Johnson. Came into the league, was a horrid free throw shooter. You know, it was like out of Michigan State. It's probably in the 70% after the first year, after his rookie year, when the Lakers won the championship. He realized, because they picked on him in that series, he could not be what he wanted to be shooting 70% free throws. So he buckled down. I think for the rest of the career, he shot 90% free throws. Do you know how many free throws I've watched Magic Johnson shoot? Thousands, probably thousands. I don't think tens of thousands. But if you give me a basketball, I'm going to shoot 5 out of 10. What's wrong? I've watched him shoot 9 out of 10, 9 out of 10, 9 out of 10. It's irrelevant what I watch. It's irrelevant what I read. I only learn by doing something, okay? So, next step. Don't just watch and read. Learn by doing. And the beautiful thing about that is as you do, you will accelerate how you learn. So at the beginning, you say, oh my gosh, this is so tedious. I won't be able to do this. But every time you do something, you do it faster, better, you move on to the next thing. Okay? That's today's motivational speech. I try not to go too heavy into those. Let's go over to the whiteboard though for a second so I can show you what I wrote there. And I wrote it there so that I could leave it up during the day so that you could refer to it as we go along. So how does this work? I just want to make sure I'm recording this for the people that are not immediately present. And then also, I don't immediately see my monitor while I'm doing this either. So I do have my speaker volume on. If you want to shout a question while I'm standing up here, just go ahead and shout it. Okay. Or get my attention if you type something in the chat, just say, check the chat. So here's the basic idea. And our mission, which is going to include Monday, is classifying linear systems. And that means if someone handed you a first order linear system, you should be immediately able to identify its trace, determinant, characteristic equation, and eigenvalues. Now, it might take you 10, 15, 30 seconds to do the quadratic equation, but there's no doubt in my mind that you could solve any quadratic equation I give you, right? So this is my analogy of the driver's license. Anytime someone hands you a square matrix, well, in our class, it's 2 by 2. These are the first 3 things you do, right? You get them on your paper right now, and you make sure they're right. You double check them so that your future calculations aren't a waste of time. And then you're still going to find you made a mistake, but at least you minimize mistakes. So it's a really important observation. Trace A plus D, determinant AD minus BC, but actually kind of magically, the trace is also the sum of the eigenvalues, and the determinant is the product of the eigenvalues. That's another safety check. So when you calculate the eigenvalues, add them, make sure it equals the trace. Multiply them, make sure it equals the determinant. So this kind of duality, sometimes in mathematics you call this kind of behavior where you have 2 representations of the same thing, duality. This kind of duality is very powerful. Okay, so then if I want to understand every linear system, maybe I could do it by just classifying by eigenvalues. And one of the handouts has that. But the problem with classifying by eigenvalues, you totally understand all the things that could happen to a quadratic equation. But still, if I ask you to write them down, it's probably more cases than you'd be pleased to look at, right? I could have 2 negative roots that are different. I could have a negative root and a positive root that are different. I can have 2 positive roots that are different. Those are the cases we worked on so far in section 3.2 and 3.3. Then today, we're going to focus on this one, which is kind of an intense calculation. I could have 2 complex roots. Now you get a little benefit when you deal with complex roots because they always come in twins, not twins, conjugates they're called. So if you have a quadratic equation and these coefficients are real numbers, then if complex roots appear, they always appear as conjugates. And this is going to be a benefit to us. But still, we have to understand what this means. Remember, the solution is eigenvector e to the eigenvalue t. So if the eigenvalues are complex numbers, how do I raise e to a complex number power? Well, you've done it before, most likely, but I have to awake that in your memory. So here are some cases. And then there's the case, what happens if the 2 eigenvalues are the same and negative? What happens if the 2 eigenvalues are the same and positive? What happens if one of the eigenvalues is 0 and the other one is less than 0? What happens if one of the eigenvalues is 0 and the other one is greater than 0? So these are other things that could happen. What happens if both eigenvalues are 0? So do you understand what I say when I say you are totally the master of any quadratic equation? And I like this word, classify. You can classify every possible answer to any quadratic equation. Usually you classify by saying there's 2 real roots, or there's 1 real root, or there's 2 complex roots. That's one way to classify quadratic equation that's useful. But I could classify quadratic equation by the nature of the roots. And each one of these natures of the roots is going to produce a different case. So let's think about it like this. I said this last time. In one dimension, there's not a lot that can happen, right? I've got phase line, equilibrium value, and I can either go both in, both out, one in, one out. That's sink source node. But in the plane, in 2 dimensions, when I have a plane and an equilibrium point, then I've got multiple ways to approach that point. I can approach from different directions. I can approach and recede. I can approach on one line and recede on the other. I can recede from that equilibrium point. I can, as you're going to see in the handout, spiral into the equilibrium point. I can spiral out. I can mix those all up. So here, I only have 3 cases. Sink, source, node. Now remember, node could have been out, in, or node could have been in, out, but it was still a node. But in a 2-dimensional case, no one can hear you scream. What's the movie with the tagline? Do you like movies? I like movies. You know, always the theater has to come up with, the company has to come up with a tagline. Like a long time ago in a galaxy far, far away. What was the movie whose tagline was, in space, no one can hear you scream? You guys know that movie. Okay, in 2-dimensional space, no one can hear you scream. No, that doesn't work. In 2-dimensional space, there are 12, 13, 15 cases, depending on how you count. Okay. So classifying the 2-dimensional space is a major accomplishment. It's not a trivial thing. Classifying quadratic equation roots is a major accomplishment too, but it's a major accomplishment you learned in the 7th grade or the 8th grade, right? So these descriptions are going to tell us what's happening. In the case of real non-zero roots, I'm going to have sink, saddle, and source. And it happened in that order, but don't think about the order, just think about the category. In the case of the complex eigenvalues, we're going to refer to them as a spiral sink, a center, and a spiral source. So spiral sink will be spiraling in, spiral source will be spiraling out, and the center will be kind of like orbiting but not going in or out. Okay? It's 6 cases. Here in the cases of repeated eigenvalues or 0 eigenvalues, what I'm going to have, and I'm going to write down the names even though the names aren't meaningful to you yet. I'm going to have an almost spiral, source or sink. I'm going to have a sunburst, source or sink. And in the green cases, we're going to have, it's not a great green pen, is it? No, I don't have good green pens. An equilibrium line. Source or sink. So still the main concept are sink, source, node, but in 2 dimensions, the variety is greater. And then here's the last case. It's kind of the fun case. It's a little bit harder to describe. So just playfully, I call it the mystery point. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are paired. 13 cases. And I said 13 to 15 because it depends on how you describe the mystery point. Don't obsess about the 13 to 15 cases, but you can obsess about putting any matrix into one of those boxes. Anytime I hand you a matrix, you should be able to instantly put it in one of those boxes. And we're going to be able to do it by the trace and determinant. Eigenvalues, possible. It's kind of cluttered and messy. But if I hand you any 2 by 2 matrix, you name the trace, you name the determinant, you put it in the box. You can do that within 10 seconds, 5 seconds if you practice. Okay, what else do I want to say? I want to leave this up because over today and maybe next day, you're going to see things fit into these boxes. The only other thing I want to say to you about this is some of these cases are major and some of these cases are minor or border cases. So we're going to bring back the word bifurcation. These are the bifurcation cases here. Even the center is a bifurcation case. But you'll see what I mean by major case and bifurcation case by Monday. I want you to acknowledge, just like people use different letters or different ways to write down trace or determinant, sometimes people use different words for describing the cases. And in fact, most commonly, sink, saddle, source, spiral sink, spiral source, center, those are common words. If you picked up another book, they might use other words, right? You got to deal with that. You got to deal with it by their description. These words that I've used right here, you're not really going to find them in the book. They're visual clues. They're visual cues to make you see what they look like. So if you remember them by these names, I appreciate it. You're going to help yourself. But you can't go to your next differential equations class and say, oh yeah, that problem number 5 turned out to be a sunburst source. Well, the instructor might look at you and say, what's a sunburst source? It's a way that we're going to describe it. It's a way that we're going to visually identify it. If you drew them a picture of the sunburst source, they say, oh yes, that's what it is. So be sensitive to the fact that not everybody uses always the same words all the time or the same notation, right? Okay. Now that we're on the same page, let's go back to our paper. And let me, let's go back to the paper and get this going. Let's do some complex eigenvalues. Okay, here we go. So you have a feeling what I mean by these points. You have the whiteboard, you have the recording. Don't obsess about everything that I wrote on the board yet. Just think about what we wrote on the whiteboard as our plan. Our plan to totally know all 2 by 2 systems. Okay, let's do an example. So you understand by now that you can do everything with the trace and determinant and the quadratic equation. But today we're going to look at the dark side of the quadratic equation. What happens if the roots are not pretty and happy, like 3 and 1, or 2 and -5, or 6 and 2, right? So let's talk about a trace and determinant that might give us complex roots. And now I'm about to show you a very important skill. Instead of writing down a matrix and hoping it has complex eigenvalues, I'm going to cheat. I'm going to work backwards and create complex eigenvalues. Isn't that the smartest way to do something? If you totally have command of something, right? Like reverse engineering the problem, let me think of two complex numbers and then put them together into an equation and then deduce a matrix that would have given me that equation. Or I could start with a characteristic equation that would produce complex eigenvalues. I think I'm going to do that. This is very much like what you would do if you were working with your hitting instructor in baseball. Sorry, I'll pick on another sport later, right? But you go to batting practice. Okay, the coach throws you a lot of curveballs because you got to learn how to hit curveballs. Throws you a couple of, whatevers, split finger fastballs because you got to learn to hit those, right? So I need you to learn how to hit complex eigenvalues out of the park. So let's take a quadratic equation that I know has complex eigenvalues. How about lambda squared plus 2 lambda plus 10. How do I know that has complex eigenvalues? Because I know what this parabola looks like. It's an ordinary parabola that's been raised up, jacked up 10 units, right? So this is not going to cross the horizontal axis. Let's see this in action. Clearly, the determinant is 10. Trick question, what's the trace? Trace is minus 2, because remember, characteristic equation is lambda squared minus trace lambda plus determinant. That's a little linear algebra fact we could talk about later. Not trace, not determinant 0, determinant 10, excuse me. So now do you see what I'm going to do? I'm going to create a matrix that has those properties. And there's lots of matrices that would have that trace and determinant. But let's just make up one. Let's make up a matrix that has a trace of minus 2. So here's a simple way to do that. How about minus 2, no, and 0? Why not? Why not? Minus 2 and 0. It wasn't what I originally wanted to think about, but isn't this trace minus 2? Yes, no one can deny that. Now I have to make a determinant of 10. So already my determinant is 0. Maybe that's why this problem is a little too easy. How could I wrap this up and give this a determinant of 10? I'm going to have a product of minus 10 here. How about minus 5 and 2? Is that a product of minus 10? So now what's the determinant? Trace minus 2, determinant 0 minus negative 10, 10. So now, even though this looks like it's just an average, everyday, ordinary matrix, I know that it has complex eigenvalues, and now we're going to be tested. So I double check my trace, minus 2, double check my determinant, 10, let's go. Well, let's do the eigenvalues. The eigenvalues of this matrix are minus 1 plus or minus 3i. We just executed the quadratic formula. If you want some entertainment, go see the video on the website that shows you how to instantly take any quadratic equation and write down its roots, no matter what. But if you want the quick speech, it goes like this. If your quadratic equation begins with a 1, you just take the opposite of half that number, minus 1, and you square minus 1 and you get 1. And 1 is 9 units short of 10. So you're short of 10, so it means you're going to get complex numbers, and square root of 9 is 3. So this roots are -1 plus or minus 3i. That's like doing the quadratic formula in your head. Go watch the video. But you can verify this if you're not sure. You can verify it in multiple ways, including multiplying them out or executing the quadratic formula. But these are two complex eigenvalues. I write them together like this because they come in conjugate pairs. If you want me to write them separate, I don't have a problem with that. Just takes extra time, and after a while, you just get used to writing plus minus. Okay, now this looks really, really bad for us because I remember my theory that my solutions are eigenvalue, eigenvector, e to the eigenvalue t. That's what I've been demonstrating so far. Eigenvector, e to the eigenvalue t. But now I got to think about how am I going to execute that right here, right? If I have complex eigenvalues, how do I compute an eigenvector? And then if I have complex eigenvalues, how do I say e raised to a complex number? What's e raised to 5i? Well, everything in order. I'll remind you of what that is. It's called de Moivre's theorem or Euler's formula, depending on which history book you read. But first, let's do the eigenvectors. So now let's calculate the eigenvectors. And by the way, you know, I know you don't do complex arithmetic every day, but actually doing arithmetic with complex numbers is easier than doing arithmetic with real numbers in many ways. So what is my philosophy here? This philosophy of building the eigenvector, so far it's worked out really good. Now I'm up against some really weird eigenvalue. What can I do? Well, it's a very common problem in mathematics. I got a new situation. What do I do? The idea is, why don't we just keep trying what worked until it doesn't work? And then in the moment when it doesn't work, I'll have to make some adjustment. But this is just like dealing with life, right? You keep doing what you know how to do. You keep doing what works, and then you make adjustments. So I'm going to look at the eigenvalue, -1 plus 3i, and I'm just going to pretend it's just an ordinary number. I'm going to do a minus lambda I for that eigenvalue. This is the adjusted matrix. And I'm going to try to find, this is what we did last time, a vector that this adjusted matrix kills. Remember I talked to you about that kind of vocabulary. Matrix times vector is 0. It's like the matrix killed the vector, or more commonly in mathematics, annihilated. This is saying this matrix annihilates that vector. Or if you did linear algebra, you say it like this. This vector is in the null space of this matrix, which means it's in the nowhere. This matrix destroys that vector. It gets sent to 0. Okay, so now what do? A minus lambda 1i. I subtract lambda 1 on the main diagonal. Let's do that really carefully. -2 subtract lambda 1. And that means I have to pay attention to the parentheses. I have to subtract that whole number. And then 0 minus lambda 1. So if you screw up the signs here, you're in trouble. So make sure you got the signs right. These two numbers I don't touch. So there's a minus lambda I there. Let's write it neatly right here. So -2 minus this becomes -1 minus 3i. This becomes +1 minus 3i. The other two numbers do not change. Let's go through our safety checks and let's go through our eigenvector selection procedure. I'm being kind of formal because I want to show you what it means to say, let's just keep doing what we were doing until it fails. What is the first safety check? That when we were doing real numbers, these two rows had better be multiples of each other. And then you say, oh my gosh, I'm screwed up. These aren't multiples of each other. Aren't they? They are multiples of each other in complex number land. These two rows are multiples of each other. They're just not multiples with a real number. If you multiply the second row by 1 plus 3i, look what happens. 1 minus 3i times 1 plus 3i is 1 squared plus 3 squared, 10. And -5 times 1 plus 3i is just -5 times 1 plus 3i. What's the first row? 2 and -1 times 1 plus 3i. So do you see that these two rows are multiples of each other? The multiple, though, is the complex number 1 plus 3i. Easy to identify because you just take the conjugate of one of these. So our new situation, complex eigenvectors, we've passed the first safety test. That means I haven't done anything wrong yet, or at least I feel that I haven't done anything wrong yet. Okay, now, second step. How do I choose eigenvector? Wasn't the procedure switch the two numbers and change one sign? Let's try and see if it works. Let's switch, and I could use first row, second row. Here I'm going to use the first row. 2 and switch these two numbers. And now just change the sign means I either make that -2 or I make this number opposite of what it is. To make this number opposite of what it is, what's the opposite of -1 minus 3i? It's 1 plus 3i. Now let's check to see if the black matrix annihilates the red vector. We multiply, and the first time we multiply with the first row, that's easy because I had switched the numbers and changed the signs. So definitely I get -2 minus 6i when I multiply by 2, and here I get 2 plus 6i when I multiply this by 2. That adds up to 0. But here, watch, I get -5 times 2 is -10, but 1 plus 3i, 1 minus 3i is +10. That equals 0. Never forget that about complex numbers. If I say to you a plus bi times a minus bi, you should not blink. You should immediately respond a squared plus b squared. It's part of what I mean by complex arithmetic is actually easier than real arithmetic. What's 3 minus 7i times 3 plus 7i? You shouldn't even blink. It's 58. It's 9 plus 49. 58. You go FOIL it out, but when I FOIL it out, all I get is a squared plus b squared. File that away. That's very, very useful. Okay, anyway, so now, well, I'm just sailing along. I got an eigenvalue, I got an eigenvector. That means I got an answer. So now I have this answer. And all I'm supposed to do is multiply the eigenvector times the e to the eigenvalue t. Now I want to remind you, I want you to acknowledge, right, that sometimes complex numbers can be ugly. I could have fractions, I could have roots. Sometimes real number roots to a quadratic equation can be ugly with fractions and square roots and irrational number, right? So it's still, in this example that we've built, is a kind of a friendly example because it's just a happy -1 plus 3i. There's no weird numbers to multiply. But now I have a problem. What's my problem? I can't have a complex answer to a real problem. Remember, how do you write this problem in its generic form? X prime equals minus 2x plus 2y. Y prime equals minus 5x. This is a real problem, a real numbered problem. It's not a damped harmonic oscillator in this case, but it's some kind of real physical situation. And if you're trying to describe the temperature of that beaker in your laboratory, you can't say, oh yeah, it's 2 plus 3i degrees Kelvin. And if you're trying to describe the position of a projectile, you can't say, oh yes, the ball is at 3 plus 2i and minus 7 plus 6i. Isn't that odd? We're talking about the real number universe. We're talking about the universe that you and I live in. Now, the complex numbers are there somewhere, right? But you can't describe your position with a complex number. You can't describe your velocity or acceleration with a complex number, not in the classical sense. On the other hand, you can't describe an electrical circuit without a complex number. And you can't describe forces or tensions in a structure without acknowledging that you might have to document complex numbers. So here the problem is, I have a real valued problem, but what I've constructed is a complex valued solution. I've run out of paper and I don't fear going to another sheet of paper, but let me write one more thing on this piece of paper. How do I reconcile this? And the answer is we can reconcile it, and it's not going to be hard to reconcile it, but it's going to be like, get your hands dirty kind of calculations to reconcile it. And so what I'm looking right now is I'm looking at the clock, I'm looking at the top of the hour. Do I want to start a crazy calculation before the top of the hour? No. So we're about to take a break. But look, this is my goal. My goal is 2 linearly independent solutions, right? That's how we used to run this. But right now I have 1 complex solution. Now remember, how are we going to solve this problem? Remember, complex numbers like, 2 plus 4i. Complex numbers are like points in the plane when you mix a real axis and imaginary axis. So here's what's going to save us. Complex numbers are inherently 2-dimensional. So I do need 2 independent answers. I need to form a 2-dimensional answer. But I have a feeling that there are 2 dimensions in this answer. And I just have to extract them. And that's what we're going to do. So before we enter that crazy calculation, why don't we just take a break at the top of the hour? Let's say, let's come back at 1:02. Do you relax, stretch your legs, and then I'll show you how to do this. Not hard. You just have to be careful with your arithmetic, complex arithmetic calculations. Okay, I'm just going to mute my microphone while I stretch my legs. Okay, we're back. I just want to, maybe you saw me writing something on the whiteboard. Just make sure everybody sees the same thing. What I was trying to tell you on the whiteboard is the first three cases, sink, saddle, source, they're presented in section 3.3. What we're doing right now is section 3.4, spiral sink, center, spiral source. And the leftover border cases, the bifurcation cases, are presented in section 3.5. And there are 6 cases there in section 3.5. They're just paired. What we're doing right now with the complex number calculation, complex number eigenvalues, is the most intense calculationally. But the plan, eigenvector times e to the eigenvalue t, always works. We just have to be creative how we describe it with the complex numbers. So let's go back to the paper. So here's my problem, complex number solution, but I have a real number problem. How do I make this work? What I'm gonna do is extract 2 real solutions from this complex number solution, pull it apart. But I have to pull it apart with some algebraic steps, with some arithmetic. So let me write this down in English. And by the way, that's kind of comforting that from this one complex solution, I get 2 real solutions. Sometimes people, because this is a complex solution, they like to remind themselves of this. They put a little C here so they don't accidentally use it. I'll put that on the other paper too. But you don't have to do that. Here's how we're going to do it. First, we need to remember what e to the I times theta means. Remember this from your trigonometry days? This is called de Moivre's theorem or Euler's formula. It's a cosine of theta plus I times the sine of theta, which is littered everywhere in engineering contexts because it's the way you describe circular motion in a way. Now, in fact, even when you look at old engineering books, you would see it this way. And sometimes in mathematics, we used to write it this way in the old days. Cis theta, which is an abbreviation for cosine theta plus I sine theta. So if you see cis theta, you know what it means. Now you would encounter this in your trigonometry course, you would encounter this in your Calc 2 course, but I'm just going to use this. I'm not going to justify it or prove it to you. It's just something you learned one day, and you can go back to your trigonometry book if you want to brush up on it. The other thing I'm going to use is just ordinary meaning of exponents, right? When you say e to the a plus b, the proper way to separate that is e to the a times e to the b. Excuse me. Not e to the a plus e to the b, So what's the rule for exponents? Common base, add the exponents. So if I put those two ideas together, I can now make sense out of a complex exponent. This is going to be e to the minus 1t e to the I times 3t. Now I rearranged that and I inserted parentheses to please myself so I can make this easier to read. But with a common base of e, this is minus 1t plus 3it. So this is that exponent. This we understand to be ordinary exponential decay. This, we remember, represents circular motion. Cosine theta plus I sine theta. That's circular motion in the complex plane. But we'll see how that comes out in a second. So now I understand that part. What is my job now? I'm going to take this complex number times these two simultaneously, these two complex numbers. And you say, no, Dave, there's only one complex number. That 2 is not a complex number. Sure it is. 2 plus 0i. That's a complex number. So think about this as here's one complex number magnifying these two complex numbers. So let's write it out. Let's do another color. So my complex solution is two 1 plus 3i. Remember, I verified that that's actually an eigenvector. We verified that right there. 2. And now, instead of e to the I 3t, I'm going to write, instead of e to the minus 1 plus 3i 3t, I'm going to write these two things, e to the minus t and e to the I 3t. I'm writing out every step. When you really do this, you're going to do it not writing out necessarily every step. Now this piece is a complex number. This piece is a real number. So let me put the complex numbers side by side because I'm about to multiply them. Cosine theta, theta is 3t, plus I sine theta, theta is 3t. And then, after I do that multiplying, I'm supposed to multiply by e to the minus t. I'm sorry, that squeezed into that box there. Okay, so let's leave the e to the minus t out on the side. Let's multiply these three complex numbers, complex number times this one, complex number times this one. So the key here is to understand that what you get is a batch of people that don't have an I plus a batch of people that have an I. Isn't that the case with any complex number? When you multiply complex numbers, there's a part with the I and there's a part without the I. So let's organize ourselves in that fashion. And if you organize yourselves in that fashion, you can all do this in one step. So for example, let's do 2 times cos 3t plus I sine 3t. The 2 times cos 3t does not have an I. And remember, there's an et attached, e to the minus t. But the 2 times I sine 3t does have an I. And I wrote the I there, so I'm not going to rewrite it. I have 2 sine 3t times I. So now I've multiplied this number times the complex number. Now let's do the same thing with the bottom number, but since I've got 2 parts, it's going to take more work. First, 1 times cosine has no I. But 3i times I is negative 3, right? So this is negative 3 sine 3t. But when I multiply these 2 complex numbers, that's the real part. The e minus t tags along. Now, what about the part with an I on it? Well, that's when the 1 strikes the I sine 3t. That'll give me a 1 sine 3t. And then what happens when the 3i strikes the cosine? That'll give me a 3 I cosine 3t. This was a plus 1 and a plus 3. Make sure you don't screw up the signs. Now let's look what I wrote in red and purple here. First of all, here's a good habit for organizing yourself. And you can call this a personal habit, so you don't have to follow it if you like. But always when you're writing trigonometric functions, I always prefer to write cosines first and then sines. Sorry, I had to move the paper. So I wrote cosines and then sines. And then I always like to keep things organized in columns. So I put the cosines in one column, the sines in another column. But this is not a 2 by 2 matrix. This is a what? 2 by 1 matrix. This is one object, cos 3t minus 3 sine 2t. These are both 2 by 1 matrices. I just organized them in columns because it was easier to write. Now, second observation. This is a real valued function. Ta-da! This red thing is only dealing with the real numbers. And if I think of the I as sitting on the outside of this function, the purple function, guess what? That's a real numbered function too, that purple function. So what I have right here, too many colors, that means I can never keep the caps straight. What I have right here is 2 real valued solutions. And that's extraordinary. Let's think about this. I started with a complex number, solutions, and I split them into part without the I, part with the I. That part that's with the I has to be a real valued solution. And I'm not going to bore you with the reason because, you know, we have a focus and a thing to do today. But the idea is that because this complex answer solves the differential equation, that means that both pieces of the complex answer has to solve the differential equation. And both of these pieces are made out of real numbers. The I is just like the separator between the real part and the complex part. So when I multiply, add, subtract, divide complex numbers, I can always separate them into a real part and imaginary part. And the imaginary part, by the way, does not include the I. So remember, if someone asks you what's the real part of 2 plus 3i, you respond 2. If someone ever asks you what's the imaginary part of 2 plus 3i, you do not respond 3i, you respond 3. It's the imaginary component, if you think in vector language. So now this is ultra cool because I've got my 2 independent solutions. Oh, by the way, how do I know they're linearly independent? Well, let's check the initial conditions. What's the value 0? When t is 0, plug it into this red thing. And by the way, I do not want to rewrite that red thing because that was enough pain. I could rewrite it, I probably will, but I don't want to write this 5 times, right? So let's put 0 into there. What do I get? 2 times cosine of 0. So this is 2 times 1, 1, 2, 1. This contributes nothing. Sine of 0 is 0. And e to the 0 contributes 1. So this is 2, 1 minus 0. 2, 1, 0, 1. So when you dust settles, you get 2, 1. What about the purple solution evaluated at 0? I have to tear off the paper so I don't push the other paper onto the floor. Excuse me. Let's put 0 into the second solution. Signs contribute nothing. So 0, 0. There's a 3 times 1, 3, 0. 0 on top, 3 on the bottom, 0, 3. Put a 0 in here, you get a 1. 0, 3, 1. You get 0, 3. Now it's time for another safety check. Where have you seen these numbers before? 2, 1 and 0, 3. These two vectors come from, and this is why if we're in class, we just let people shout things out. And you can shout things out if you like, but there's this time lag problem. These two vectors come from the complex eigenvector. Where did I see 2, 1, and 0, 3 before? Right there. 2, 1, 0, 3. I even wrote the 0 right there. 2, 1, 0, 3. So now it's safety check time. If you get down to here and you don't see your complex eigenvector represented, you screwed up. But that's okay, because then you just go back and fix it. So now I have my general solution. And by the way, I'd much rather write it like this. K1, Y1 of t plus K2, Y2 of t. There's absolutely no way I'm going to rewrite these. Well, I mean, there is a way I'm going to rewrite them. I am going to rewrite them. But you see, I don't want to rewrite them many, many times, right? So let's go for a solution through, and then we're going to run this into Mathematica. Let's go through a solution to this problem through some initial value. Let's take an initial value of -3, 1. So now let's rewrite the problem. What was the original problem? -2, 2, -5, 0. And y of 0 is -3, 1. You see how harmless this looks? Just looks like an ordinary problem. Of course, we've already worked out that I've got these fancy complex solutions. But my first step is, what's the ratio? What's the balance between those two solutions? So what I have to do is take the 2, 1, and K2 times 0, 3, and I have to see how many of these each do I need to make this. Now remember, this is the time when I said to you 0 and 1 are your friends. So this 0 right here means that K2 contributes nothing to that -3. So now I know K1 is -3 over 2. Because -3 over 2 times 2 is -3. Okay, now, since I know that, I can run that right over to K2, right? So this is minus 3 halves times 1 is contributing minus 3 halves, but I need plus 1. So to get from minus 3 halves to plus 1, I've got to add 5 halves. That's not pretty, is it? I've got to add 5 halves. So what is it that's going to turn 3 times K2 into 5 halves? 5, 6. 3 times 5, 6 is 5 halves, plus minus 3 halves is 2 halves. I am not saying in any way that you should only do things like this in your head because you're going to double check them, right? But I'm saying that because of that 0, this is not horrid. But if my eigenvector would have been unpretty, roots, things like that, this would be more work. So remember, I'm just doing a basic problem. So now I know my special solution is minus 3 halves y1 of t plus 5, 6 y2 of t. But now I'm not going to be able to avoid writing down the individual pieces. So I'm going to have to go up here and take the y1 and y2 and bring them down to here. It's very hard to do that in one screen. Well, let's give it a shot. 2 cos 3t, it's not impossible, I just have to be organized. Cos 3t minus 3 sine 3t. E minus t, don't forget that. We'll tell you what it's doing in a second. And then 5, 6 times 2 sine 3t, 3 cos 3t, plus sine 3t. That's the horrible mess, right? But no i's. So it's just a matter of me bringing all the pieces together. So minus 3 halves times 2 coses is minus 3 coses. Over here, I got no coses. So I have minus 3 cos 3t. But I have no sines here, and 5, 6 times 2 is plus 5/3 sine. 5/3 sine 3t. You see, I'm bringing this together in one function. Now let's look at the bottom. Here's a minus 1.5 coses, and here is 5, 6 times 3, 5 halves coses. So what's minus 3 cos, minus 3 over 2 cos, minus plus 5 over 2 cos is positive 2 over 2 cos. Hard to speak things like this. That's cosine 3t. And now I have plus 9 halves sine plus 5, 6 sine. Now 9 halves is like 27/6. Right? So this first thing is positive 27/6 sine, positive 5, 6 sine together, positive 32/6 sine 3t. That does not simplify. Boy, I sure hope I did that right. Safety check. Now, this doesn't prove I did anything right, but do you see that when you put in t equals 0, you do get minus 3 and 1 for your initial value, which is what we wanted. So at least I got the initial value straight. Now let's talk about the quality of this solution. What do we have going on here? We have 2 people getting together, 2 very different people. This person right here is called exponential decay, right? And this people is a sine wave and a cosine wave added together in the x position and the y position. So I could say that I actually have the X and Y solutions here. And again, I hate writing this because it's too much writing, but I think I'll do it once. I hope I wrote this correctly. Well, we're going to find out in a second when we graph it with Mathematica, right? And here's the y component, cosine 3t plus 32.6 sine 3t. But what happens when you add a cosine wave and a sine wave of the same frequency? Angular frequency 3. You get another sine or cosine wave. That's a concept from trigonometry. When you add two waves of the same frequency, you get another wave of the same frequency. Excuse me, I have to move that up. So what I have here is oscillation and decay. What does it mean to have oscillation and decay? Now, my initial value was minus 3.1, which is over here. Oscillation and decay means I am going around the origin and I'm getting smaller and smaller every second. I do not know about my scale. Sorry. The scale could be different, but I am oscillating, going around the origin and decaying. I could be going this way. I could be doing some extreme flat oscillation. That's going to be determined by all these numbers. But the core is that I'm either going counterclockwise or clockwise, and I'm clearly decaying because the E minus T. Now, all this is worthless unless we reproduce it in Mathematica. Oh, by the way, I can tell right now whether it's counterclockwise or clockwise. Let me show you how. Take my initial value, minus 3.1, and multiply it by the matrix. Because what happens when I multiply my original matrix times minus 3.1? I learn which way I'm headed at that point. Let's try this out. When I multiply, what do I get? I get 6 and 2 is 8. Here I get 15. That's a crazy vector, but it's like 8 over and 15 up. Well, I'm not going to go 8 by 15, but it's almost 2 to 1, right? So this vector is going over and up. Does over and up mean clockwise or counterclockwise? You see how poor these drawings are. But the only way to go over and up when I'm sitting right here is to go clockwise around the origin. So now I know that it's clockwise, and I even have a feeling for the scale. It might be kind of tilted like this. Let's find out. Okay, so we're going to share screen. We're going to go to first order linear systems, Mathematica notebook. Remember I said this one notebook will do it all for you in this chapter. Cap all my pens so I don't inadvertently tattoo myself. So here's my thing. Let's put in this matrix. What was this matrix? Minus 2. You can write your own notebook. I have no problem, but until you're comfortable, you can use the one I provided. And remember how quickly Mathematica does this? So let's check out if we're right. The trace was minus 2, the determinant was 10. There's my equation. There's my characteristic values, my eigenvalues. There's my eigenvectors. And remember, eigenvectors, you have freedom to choose. So we chose 2 and 1 plus 3i, but the machine chose 2 other legitimate eigenvectors. Notice, by the way, I didn't have to do 2 eigenvector calculations. 1 was enough. Now, here's an interesting thing. you're going to say, back to the original problem, I'll go back to my paper, I'm sorry. What would have happened if you would have chosen the other eigenvalue, David? I would have got a different answer. But the answer is no, you wouldn't. And I have a handout on the website that shows you that whichever one you choose, in the end, you arrive at the same answer, the same two components. Your calculations will look different for a short time, but you have to arrive at the same answer. So thankfully, I didn't have to do two of these. And thankfully, I don't have to remember which one to do first. But I'll tell you, always choose the one with a positive imaginary part, because then you avoid doing some trig identities. Okay, let's get back to our Mathematica notebook. Make sure I number my papers. Let's see how good my spitball drawing is. Okay, so back to Mathematica notebook. So initial condition for this problem was -3 and 1. So I'll input this. I have to input this to feed this information to Mathematica. Oh, some of you even showed me notebooks with this. Null. Look at the response by Mathematica. Null. That can't be a good response. And null in general means there's nothing there, right? Computer science or math. What the null set is the empty set, right? What it means is I've screwed up a character. I don't know if you see those little red dots right there. Somehow I typed a special character or I typed something wrong on my keyboard. Let me erase that. And let's hit Shift Enter again. Okay, now Mathematica does not complain. Okay, now we're gonna have everything together. Here's our system, which is the same system as I wrote out. Notice it's nice that I write this out in full detail right there. And let's talk about streamlines. What do we got here? I'll have to put in points later, right? But I'm already going through -3 and 1. Let's get it together and see what happens here. Look at that. It is a clockwise spiral. And it's just not as much oscillation as I felt, but it's got that angle to it, right? That over 8, up 15 direction to it. Excuse me. I don't like these red arrows and red solution. So let me go back and fix that. Let's let my vectors be blue, or let's let my solution be blue, vectors be red. There we go. And you see the solution, it's going through -3 and 1, which I could add a point for -3 and 1 if you like. But, and you see it fitting beautifully the direction field. Now I want to emphasize the individual solutions right here, that these are oscillation and decay. So individually, what does oscillation and decay look like? Back to Mathematica notebook. Let's ask Mathematica to draw the individual x of t and y of t. Oh, by the way, Mathematica is going to work out the answer. There's the answer, right? Now, if you multiply this out, it is exactly the answer we wrote. Oh, look at that. See, I said 32/6 and I didn't touch it. Mathematica said, hey, Dave, it's 16/3. Okay, so I can always learn something, right? Okay, but this is the exact answer we had. Now let's plot the x of t and y of t solutions. Everything's been pre-fed to this. Maybe I'll have to change parameters of space or, window. Let's try it. There is my curve in the plane. That's a parametrically defined spiral. And here's my oscillation and decay. Both x and y oscillate and decay. I think I like a more longer window. So instead of 2 seconds, since I'm doing, by the way, you see this solution here, I'm doing that exactly. I'm not doing it numerically. So let's run this to 8 seconds in time. I think 6 might be okay. Yeah, oscillation and decay until what? Both X and Y land at 0 and 0. Awesome. Okay, so I've got a little bit of confirmation going on here. Well, quite a bit of confirmation. So I feel comfortable with my answer. It takes a while to feel comfortable with complex answers till you practice doing the complex arithmetic. Let me show you one other cool thing on our website. So share screen, website, where is it? Right there. On this week 3 page, we're looking at our week 3 page right now. Under technology, I have a cute Desmos demonstration, graphs of spiral sink, spiral source, and centers. So I've got too many things turned on at once. So I've got to make sure I see what you see. Okay, good. So here, first of all, I'm getting dizzy, so let's stop it. But in this drawing, what I did is wrote down some generic equations for spiral sink, spiral source, center, A, B, C, D, and then I let you play with the A, B, C, D. I let you play with the A, growth or decay constant. I let you play with the omega, which I used a W here. And by checking out the growth or decay constant, you can make this go to 0 very quickly, or you can make this go to 0 very slowly, or let's put A is 0. What happens when A is 0? You just have a center, eternal oscillation. Now, when A is positive, you're going to be spiraling out, getting bigger and bigger oscillations. Okay, let's do the same thing with omega. Different omegas give me what? Different number of oscillations about the origin. What did the ABC do? ABCD changed the tilt and orientation of this object. Now, this is not important. I'm not asking you to do these calculations. I'm asking you to visualize what happens when you have complex solutions. Okay, that's the visualization. You can play with it. I'm not representing our problem here because I didn't fill out the ABCD, but I could take the ABCD from our problem and the A from our problem and make it match here and see if I match my mathematical graph. But I'm not going to play with that right now. Okay. This was the complex eigenvalue calculation. It is the most intense calculation we're going to see in chapter 3. Okay? But I don't want you to be, put off by it. All I'm doing is doing complex arithmetic very carefully. Notice I got plenty of safety checks. I have plenty of ways to verify my answer. And remember, I said this to you in email at the beginning of the week. The first question on the test said, show me that it works. But do you understand, in a way, every time you write down an answer, you should be showing yourself whether it works or not. Never, ever write down an answer without checking to see if it works. Now, I understand there are time constraints, there are space constraints, so sometimes you don't check, right? Then you pay the price. I pay the price. But I'm saying this is why you study math. Well, okay, I know some of you are studying engineering. This is even why you studied engineering in a way. Somewhere along the line, you can verify it. And that's different than history. And that's different than psychology. You have two different theories of the Napoleonic Wars, right? And who's to pick between them? course, you can throw out crazy historical theories, depending on your definition of crazy. This is math. This is engineering. This is science in the general sense. There is a correct answer, and you can know whether you're correct or not. I enjoyed physics. I thought I was going to study physics when I entered college. I thought that would be like totally cool. But somewhere after the sophomore year, I started doing this quantum mechanics stuff like, well, we're not sure if this particle is there. We're not sure if this particle is there. Oh, we're not sure if this particle exists or maybe it doesn't exist. And by the way, we got this problem with lots of leftover matter. I got very, very nervous. Like, I'm just being silly, but I wanted certainty, right? And in the math classes I was taking, there was always an answer. Even if it was ridiculously difficult to do, there was always a correct answer. Okay, so I switched to math. You study what makes you feel good. But I'm saying at least here, whether you like math or not, you got some certainty. Okay, now we got to talk about the special cases. And in a way, section 3.5 and 3.7 are going to go together. So the things that I'm going to say today, and I'll do more examples from 3.5 tomorrow, they won't make total sense till you've seen 3.5 and 3.7 together. And that's why I put 3.7 ahead of 3.6, so you could put the puzzle together first. But I could give you just a simple example. Let's say a simple example that I could work out here in 5 minutes. So let's say I got this going on. Here's a matrix. And let's say I got 6 and minus 2. And let's say I got 2 and 8 negative. Now, you know, by the way I selected those numbers and the way I wrote them down, that I must have been preparing something. I did not write down random numbers. I hope I wrote down good numbers. This is very much like a magician, right? When a magician says, oh, just take a card, any card, he or she's already prepared something, right? In fact, the act of being a magician is to do what? That she doesn't show you what she's preparing, that she delivers it in a smooth fashion so that you don't see what she prepared. So you actually saw me write down the 6 and then the minus 2 and then the 2 and the minus 8. So what do you deduce from that? In my mind, I was concentrating on the trace and determinant. But let's play it like a straight magic trick. To you, this is just a matrix. Take a matrix, any matrix, right? What's its trace? 6 plus negative 2 is 4. What's its determinant? Negative 12 minus negative 16. Now that's negative 12 plus 16 is also 4. So remember, you are the unsuspecting mark. It was a kind of a nice movie. I'm a movie buff too. Now You See Me. Is that the movie? Woody Harrelson. Throw some other names in the chat if you're Woody Harrelson, Mark Ruffalo. Now You See Me. It was kind of a fun movie. Was that, do I have the title right? Okay, lambda squared minus trace lambda plus determinant equals 0. It's a quadratic equation. It's not even a hard one, right? In fact, you can factor this. I don't need any stinking quadratic equation. Oh, by the way, I can also do this immediately in my head, right? Half of the opposite of that number is 2. When I square 2, I get 4. I am not short of this number. I am not past this number. So I'm going to do plus or minus square root of 0. And so this quadratic equation only has one root, which is 2. Now, I'm going to pretend as if there are 2 roots. Because I'm thinking about how it factors. So I'm not going to get into any argument here, like, is there 1 root? Is there 2 roots? Okay, is it 1 root with a multiplicity of 2? Let's not get into any fancy words. I only have one eigenvalue. I only have one value, same value repeated. And then what do I fear? Oh, shoot, I need 2 solutions, but I only have one eigenvalue. Okay, remember our philosophy that we used successfully in the complex case. Plow ahead, use your method, trust your method. Let's see what happens. So let's go a minus lambda I and find my eigenvector. So I subtract 2 on the main diagonal, which produces 4, 2, minus 8, minus 4. I'm just writing this down so you physically see the eigenvector. Safety check, are these 2 rows multiples of each other? Yes, they are. Okay, I feel good. I'm going to select an eigenvector now. I'm going to select 1 minus 2. The ratio is 2 to 4. Remember, switch number, change sign. But I'm going to select 1 minus 2 instead of 2 minus 4. Remember, tip number 1, reduce the numbers. Use reduced numbers if you can. So here's my eigenvector. For my eigenvalue, 2. And this much looks good. I have a solution. And so this is going to have to be the last thing I could squeeze in here. But where's my second solution? Remember, I'm in a 2-dimensional case. I'm in the plane. I'm in the 2-dimensional plane. That means I have to be able to go through any point in the plane. Now, by the way, you saw in the case of the complex numbers, I can touch any point in the plane with that spiral, right? That spiral is the combination of 2 independent solutions, even if they're not straight line solutions. But here, this is a straight line solution. How am I going to touch the other points in the plane? How am I going to get to them? Well, now, unfortunately, I got to use some fancier linear algebra. Fancier in explanation, not fancier in execution. So if you really want the full experience, I seriously urge you to take a linear algebra class. But let's look at my situation right here. I succeeded in finding an eigenvector. Now, I want to talk about philosophy with you. The eigenvector is the vector that the adjusted matrix kills. But my problem is, I can't just select a copy of this. That won't be independent of this solution. If I select 2 and minus 4, or minus 4 and 8, I'll just be on the same line through the origin. So I need to find another independent vector that this matrix kills. But because I've only got one independent eigenvector, let's think about the vampire movies here. Let's think about the Underworld series, whatever you like. It's going to take multiple shots to kill this thing. In other words, I found the easiest eigenvector. Now I got to pick off a different one. So here's the trick. This is a linear algebra trick. And I can tell you about the reason I do it. But if you want to know exactly why it works, you got to take linear algebra one day. Let's slide the eigenvector over to the other side. Instead of 0, 0, let's go for the eigenvector. Same adjusted matrix. And now I want you to give me a vector that gets sent to the eigenvector. And I'm going to playfully call this an almost eigenvector. If you read the notes at the beginning of the week on our webpage, the technical word is a generalized eigenvector. But I can say it to you in plain English. Here's the plain English. An eigenvector is a vector that gets killed by one shot. Bang, it's dead. But a generalized eigenvector is a vector that gets killed by two shots. Bang, bang. Because the first shot turns it into the eigenvector, and the second shot kills it. Isn't this all the case in the vampire, the werewolves, the zombie movies? First, the zombie is completely undefeatable, or the vampire is completely undefeatable, right? So the hero has to turn the vampire into a pumpkin, and then he smashes the pumpkin. Or it's something like that. I don't know what movies you watch. But first, I'm going to take the eigenvector. If I can find a vector that I can turn into the eigenvector, then I know I can kill the eigenvector. This is called, in fancy linear algebra class, generalized eigenvector. Now, your first reaction is, boy, it was easy to pick that eigenvector. How am I going to pick this one? And the answer is, it's also going to be easy to pick this one. You just got to study this for a second. Look at 4 and 2. Look at the -8 and 4. And now I'm going to use this word. 0 is my friend. So if I made one of these slots 0, I don't care which one. Let's make this first slot 0. How in the world could I produce a 1 there? 4, 2 times 0 something going to make me a 1. What do I got to put here? I have to put a 1/2. Is that true? Is that really going to work? Is that all I have to do? Let's try -8 minus 4 times 0, 1/2. What does that produce? -2. Ta-da! 0, 1/2. Generalized eigenvector. It is not killed with the first shot. But if I do 2 shots, the first shot turns it into a vulnerable vector. Second shot kills it. And now here's my second solution. Be careful. It's not easy yet. We're not safe yet. It's like after you do the steak and the vampire, whatever, the movie calms down, the music goes quiet, and then the vampire lurches to life, right? So there's one more thing I got to do carefully here. To make the second solution, I have to take t times the eigenvector. I'm trying to color code things. Plus, then I should have done a different color to start with, right? The almost eigenvector, the generalized eigenvector, and then the e to the 2t. This is enough to give me the independence. Notice when I put in 0 here, what do I get? I get the generalized eigenvector, 0 and 1/2. And that is independent of y1 of 0, which is 1 minus 2. It's not fair for me to do this so quickly. you've got to see it in action. You've got to see the drawings. I think that's what we're going to do today. This is the most important of the special cases. This happens to be what? It has to be a source because I've got growing exponential. But I don't have two straight lines. It's called an almost spiral source. What I have is one straight line at 1 minus 2, and I have curling into that straight line. Let me take a point like 1, 0 and test the direction. 1, 0, I get 6, 2, which is like that. So I get curling out, curling out. So I get a source. Everybody's going away, but it's only got one straight line, and it's trying to spiral, but it can't spiral because it hits that straight line wall. Pop that into Mathematica, see the graphics. You'll be a little bit more comfortable, but we're going to do examples of that next time. Okay. A question unanswered is now, why do I say they're special cases? And this is where I said to you at the beginning, everything we learn in chapter 1 is going to come back to help us or haunt us. And what's coming back is these special cases must be the what? The transitions between the major cases. These will be the bifurcation cases. So next time, let's finish up 3.5 by showing you what I mean by the bifurcation cases, and you won't really see it until we're done with 3.7 on Monday. Okay, you guys relax. You have a good day. Hand in a couple more homework problems. I'm going to turn off the recording. You can hang out for a second if you want to ask a question.